Continuing on with the idea of divisibility and greatest common divisors, we have the following theorem. So let a and b be integers, not both 0, and let d be their greatest common divisor. So again, greatest common divisor, d has to divide both a and b, and if there's any other integer out there that also divides a and b, it has to be less than or equal to d. Those two conditions need to be met. Then there exist, and here's the big part, not necessarily unique integers, u and b, such that we could write the greatest common divisor d as a linear combination of some scalar, in this case some integer, some integer u times a plus some integer v times b. Now the question is, well, how do we find this summation here? Well, basically what we're going to do is we're going to use the Euclidean algorithm and just work in reverse. Now I do want to be really clear about this theorem. So the fact that d is equal to au plus bv, this does not imply that d is the greatest common divisor. So if we started here and tried to work our way backwards, this wouldn't work. So how the theorem works is that we already know that d is the greatest common divisor. So if d is the greatest common divisor, then there's integers u and v, again, not necessarily unique, such that we get this summation here. So let's jump back to our last example and see how could we find this. So we ended up with the greatest common divisor of 78 and 30 was 6. So based upon this theorem, I know it's equal to 6. I should be able to write 6 as I'm going to have some, I'm going to take 78 times some scalar, we'll say, I'm going to use the same one that we had here, u, plus 30 times v. Now the question is, how do we find this u and v? Well, again, as I said, we're going to use the Euclidean algorithm just in reverse. So how do I start this process off where I can write the greatest common divisor as something? Well, if I notice my last line here in the Euclidean algorithm, I have 18 is equal to 1 times 12 plus 6. So if I reorder that, I rewrite that as 6 is equal to, now I'm going to move that 1 times 12 to the other side. So this is going to be equal to 18 minus 1 times 12. Now notice this 18 and 12, these aren't my original numbers. My original numbers were 78 and 30. But these 18 and 12, these are my remainders that I've gotten through various iterations of this algorithm here. So in order for me to get rid of the 12, what I'm going to do is I'm now going to move up one line. So I started the second last line of my algorithm. Now I'm going to move up one line from there, and I'm going to isolate that 12. So 12 is equal to 30 minus 1 times 18. So I'm going to plug that in. So 18 minus 1 times 12, but 12 is really 30, minus 1 times 18. And let's simplify this out a little bit. So this is 18 minus 1 times 30 plus 1 times 18. And I can write this as, I have one factor of 18 over here, 1 over here, so this is 2 times 18 minus 1 times 30. So now I do have a 30 in here, good, but I now want to get rid of this 18. So in order for me to get rid of this 18, again, I go back up and I use information from previous iterations to get rid of the remainders. So from the previous iteration, this tells me that 18 is equal to 78 minus 2 times 30. And if I plug that in here, this is 2 times 18, which is really 78 minus 2 times 30 minus 1 times 30. And working this all out, what do we get here? This is going to be 2 times 78. I'm going to have a minus 4 times 30. And I'm going to have a minus 1 times 30. So this is 2 times 78. Let's use round brackets instead so it doesn't look like I'm dealing with decimals here. Minus 5 times 30. So my 78, my 30, these are my original ones. So this tells me my u is equal to 78. My u is not equal to 78. My u is equal to 2. and my v is equal to -5. And that I would just plug into here. So that's how we do it. We just do the reverse of the Euclidean algorithm. Now a corollary that we get from this, so again, let a and b be integers, not both 0, and d is some positive integer. Then d is the greatest common divisor of a and b if and only if d satisfies the following conditions. So d has to divide both a and b, perfect. And the second condition is that if there is anything else that divides a and b, so if there's a c that divides a and there's a c that divides b, then c also has to divide d. So it's no longer stating that c has to be less than or equal to d, I'm saying that c has to divide d. Okay, so we're not going to prove these two things here. If you want to try and figure it out, that's a good exercise to work on. But this leads us now into our next theorem. So our next theorem, and we're going to prove this one because it's going to help us solve the next exercise. So in this case, we have two conditions. So if a divides bc, so the product bc, and the greatest common divisor of a and b is equal to 1, then a has to divide c. So let's go ahead, let's prove this one, because this is going to be, as I said, the technique for this is going to be the technique that we're going to use to solve the next problem here. Now you'll notice going through this, we're not going to prove absolutely everything in here. We're going to use a lot of these theorems, but we're not going to be proving all of them. All right, so this is proof of theorem. Okay, so what are we given in this case? We are given that a divides bc. Now what does this mean? That means that bc can be written as some a times x for some integer x. And we also have that the greatest common divisor of a and b is equal to 1. Well, what does this mean? Well, from that previous theorem, we know that we could write 1 as a combination of a times u plus b times v. And now what we want to show, I'll write this over here, is we want to show that a divides c, which again, this means that c could be written as some a times y. Okay, so let's work this out. Given the information we have, we're going to start with the 1 is equal to au plus bv. And now I'm going to multiply both sides by c. So this is going to be c is equal to au c plus bv c. Now I can rewrite this auc plus, because again, this is just a product of integers, which is perfectly fine to reorder them. We can do that with integers. So I could write this as bc v. So I've used the first condition here. Now I need to use this second condition here. So the second one, where a is divisible, or a divides bc, then I can write bc as this a times x. So every time I see bc, which I see it right here, I'm now going to substitute in ax. So c is equal to auc plus, instead of bc, I'm going to write this as axv. Now notice both of these terms have an a in it on my right-hand side, so I can factor out that a. So this is a times uc plus xv. And if we let uc plus vx equal to y, then this is c is equal to ay, which implies that a divides c. That's our proof. So again, we needed both bits of information there for this to hold true. As I said, this is going to help us on this exercise here. So suppose, in this case, that the greatest common divisor of a and b is 1. Now, if a divides c and b divides c, we want to be able to prove that The product of A and B also divides C. So to prove this one, again, we're using the same techniques that we did beforehand. So this is exercise 4. So we're given that A, B, the greatest common divisor is equal to 1. We're given that A divides C, and we're given that B divides C. So for this A divides C, that means I could write C as equal to some A times M. And here I could write C is equal to B times N. So now, based upon this division, I have two ways of being able to write C. And again, starting off with this condition here, the greatest common divisor of A and B is equal to 1. That means I can take 1 is equal to A times U plus B times V. Now, what do I want to do? Same as before. This is why I did that proof. I'm going to multiply all the sides by C. So this gives me C is equal to AUC plus BVC. Now our goal, we want to be able to show that AB divides C, or we could write this as C is equal to AB times some, we'll call this again Y. So basically what I'm looking for here is I want on my right hand side, I want in both of those terms there to be an AB factor that I can take out. So in the first term I have an A, but I don't have a B. But I do have a C, and I know I could write C being equal to BN. So that's what I'm going to do. So AUC, but I'm going to write this as BN. Plus my second term has a B in it, but it doesn't have an A. It does have a C, and I could write C as AM. So this is BV AM. And of course, I could reorder this because this is all just product of integers. So this is AB UN plus AB BM, which I could write as C is equal to AB times UN plus VM. And if we let Y equals to this sum, this UN plus VM, then I get C is equal to AB times Y, which is exactly what I needed to show. Therefore, AB also divides C.